All right, today we are diving into a real scientific detective story. We're on the hunt for a ghost, a phantom signal that was hiding deep inside the data of one of the most sensitive instruments you can imagine.
I mean, think about it. This is the fundamental question that a team of scientists was grappling with. When you're looking at the atomic scale, a world so tiny that the smallest vibration can look like a giant mountain, how do you possibly tell the difference between a real feature and, a trick of the machine? So before you can even ask a question like that, you need a way to see this invisible world in the first place. And for that, scientists have an absolutely incredible piece of tech. It's called an atomic force microscope, or AFM for short. And the key thing to understand is that it doesn't really see with light the way we do. Instead, it feels the surface. The best way to picture it is to imagine a record player's needle, but one that is so unbelievably sharp it can trace the actual outlines of individual atoms. That's what we're working with here. So how does this whole thing work? Well, it's kind of like a beautiful three-step dance. First, you have that super sharp tip scanning back and forth across a material. Second, a laser beam is constantly bouncing off the back of that tip. So any tiny movement, even the height of a single atom, changes the laser's angle ever so slightly. And finally, a computer tracks that changing angle and uses it to build this incredibly detailed 3D map of the atomic landscape. It's simple in concept, but just staggeringly powerful in practice. Okay, so that's the tech. But this is where our mystery really kicks off. Because when scientists used their AFM for what should have been a very simple, very boring task, the picture they got back was, well, it was weird. The mission seemed totally straightforward. Just look at a sheet of mica. Now, mica is cool because you can split it into these atomically flat sheets. It's pretty much the smoothest, most perfect surface you can find, which makes it perfect for calibrating a microscope. The plan was to take 4 images, starting with a wide view and zooming in tighter and tighter. They were expecting to see basically nothing, just a flat, boring surface. But that is not what they saw. When they pulled the raw data from those images and looked at the numbers, there was something else hiding in there. An anomaly, a ghost in the data that just shouldn't have been there. The investigation turned up 2 huge clues. Clue number 1, that whitest image, the one that should have been perfectly smooth, looked really rough. That was a big red flag. But clue number 2 was the real smoking gun. In the 3 most zoomed-in images, they saw the exact same pattern of strange, repeating spikes in the data. Now, that should be impossible. At different zoom levels, the patterns should look different, but these matched perfectly. And that led them to the central question of this whole mystery. Were these spikes a real physical feature on the surface, something that exists in space? Or were they some kind of illusion, an interference happening over time? This really boils down to 2 possibilities. On one hand, you have a spatial feature. That's a real bump or a real valley that's physically part of the mica. If you scan over it again, it's going to be in the exact same spot. But on the other hand, you have time domain noise. This is something else entirely. It's an external vibration, maybe a fan in the building, maybe a truck driving by, something that's making the microscope's tip wiggle. It isn't part of the surface at all. It is literally a ghost in the machine. So to solve this, the scientists had to figure out a way to separate space from time. And the experiment they came up with to do it was absolutely brilliant and incredibly simple. Their idea was pure genius. They thought, what if we just stop moving? They told the microscope to lower its tip to the surface and then just hold it there, perfectly still. No more scanning back and forth, no movement in space. All they were going to do was listen in time. This one simple test would force the ghost to show its hand. The logic was pretty much inescapable. Okay, think it through with me. If those data spikes were from a real bump on the surface, a tip that's just sitting still in one spot would never see it move, right? The data signal would just go flat. But if the spikes were caused by a vibration, a noise happening over time, then the tip would still be wiggling up and down from that vibration, even while it's standing still. The phantom spikes would still be there. And when they ran the test, bingo, that's exactly what they found. A clear, steady, repeating signal, a vibration with a very specific frequency, 328 hertz. This was the ghost's voice, loud and clear. The case was officially closed. Just as the researchers put it, the spikes from their original scans were a perfect match for the noise they recorded with the stationary tip. They had captured the ghost. It was never a feature on the mica. It was a vibration in the room the whole time. So yeah, a really fun detective story, right? But the reason this is so cool is that the implications of this simple test are actually huge for science and technology.
You see, this stationary tip test is way more than just a clever trick. It's an incredibly powerful diagnostic tool. It gives scientists a simple way to proofread their data, to separate what's really there from what's just environmental noise. And that is absolutely critical when you're doing things like designing the next generation of computer chips or developing new medical devices. It gives you a way to find and hunt down the ghosts in your lab before they trick you into seeing things that aren't there.
By learning how to listen for these tiny phantom noises, these whispers from the machine itself, we're not just cleaning up old data. We're opening the door to getting a fundamentally clearer, more accurate picture of the atomic world than we've ever had before. And it just makes you wonder, what new discoveries have been waiting there all along, just beyond the noise, for us to finally see them clearly?